We present a visual analysis approach for defense construction against inference attacks on sensitive information. When examining a data set, we can speculate conclusions by inferring from other factors. For example, in a medical data set, an individual is likely to be unhealthy if they demonstrate high medical expenditure. Similarly, adversaries can extract inferences from datasets, reports, or common senses, and infer the sensitive states of individuals from a supposedly sanitized dataset. In other words, it's not enough to merely remove sensitive information before publicly sharing the data. As a solution, in this work, we simulate adversaries' background knowledge and interactively recommend appropriate processing schemes that protect sensitive information from disclosure. Our approach has 3 stages. In the inference initialization stage, users define states according to data distributions. We extract underlying inferences through conditional probabilities and construct an inference graph. In the data processing stage, we group data records with the same states together. Because they involve the same inferences, they can also share solutions. For groups with a risk of privacy exposure, the system recommends solutions and demonstrates how they will work. The final stage is result verification, where we summarize the distribution of the processed data set. To maintain distribution ratios of the original data, users can apply trimming schemes. We additionally support attack simulations based on other models to determine the level of privacy preservation. We design a corresponding interface for each stage. Since we process along 3 stages, our system has 3 main interfaces. We start by employing an inference graph to simulate adversaries' inference bases. Here, nodes refer to states. We label states defined by the same attribute via convex holes. Edges between nodes depict underlying inferences, which may potentially be employed by adversaries. In the data table view, we show the privacy exposure risk for each group. Groups with alternative solutions are highlighted by black triangles. States that need to be removed are covered by stripes. For result verification, the data trim view allows users to verify data distributions and evaluate the processed data's resistance to other simulated attacks. Let's show our system through a case study. The student dataset consists of 480 students, having information about their backgrounds, behavioral factors, and their parents' satisfaction status. We start by selecting 9 attributes in the dataset and marking the class attribute as sensitive. Then we set the privacy exposure limit to 0.3. In the first stage, inference initialization, we edit the split points of numerical attributes based on their values distributions and merge 12 categories with less than 25 samples into a data point called Other for the place of birth attribute. Edges in the inference graph can be filtered. We click on an edge to check probability details. Users can modify the inference graph by editing these probabilities. Next, we click a sensitive state representing performance rating is low and check its conditional probabilities in the state set chart. We find 2 single state sets, absent more than 7 times and visiting the course content less than 50 times, outside the no risk zone. The 2-state set with the highest exposure risk also contains these 2 states. Actually, most sets with privacy exposure risk contain 1 or 2 of them. To simplify the inference graph, users can merge states by attributes. Here, we can unfold an edge by clicking. After observing the correlations between attributes, we set the utility values for the attributes based on the length of the path from each attribute to satisfy. With the sources of privacy exposure identified in the first stage, our system moves on to the second, which recommends removing about half the values of the visit res and absence data attributes. We click the bar to stick these records that need to be removed for the absence state. After comparing alternative solutions, we change solutions for partial records in group 1. In the third stage, results verification, we simulate an attack based on random forest. Seeking a better preservation strategy, we leverage trimming schemes for raise hand and discuss attributes. We found that the probability of privacy leakage decreases after trimming a minority of the states. Now the data can be safely exported and shared with other groups. Thanks for watching.